Welcome, welcome, my general chemistry class. I love it. We are getting near the end of our topics. This is our gas laws. This is video 2 in a series of 3. And this one is dedicated to just sample problems. So definitely watch the first gas laws video first. We're going to define everything in that video. Grab your calculator and your unit conversions and let's have some fun with gases. We're going to do just problems. And I broke this up into 2 videos. This first video is just getting to know our ideal gas law. Okay. This one is all our ideal gas law. And we're going to apply it first to just some problems, and then our next video, we're going to apply it to chemical reactions. So we're going to kind of combine a little bit of every unit from this semester. It's going to be so much fun. So how do you make gas laws hard? 2 ways, funny wording and unit conversions. So I have a little sprinkle of that in this video. I'm going to do 4 problems with you today, so if you want to take a second and write out that problem, let's do it. I also want to show you my method for gas laws because really the 2 ways to make them hard are funny wording and wacky unit conversions. I've got my unit conversion table here with me, and I like to spell out gas law problems the same every single time. It sounds corny, but that eliminates the wacky wording. So I'm going to take my ideal gas law from our last video. That's our PV equals nRT. And I just spell it out. And I spell it out while I'm reading the problem. Again, sounds silly, but it's going to save you time in the long run. Because then as you spot what you've got in your question, you just put it right in there. Fill it in. So we've got 2.54 moles of an ideal gas. Oh, we've got 45 degrees Celsius. And we've got a volume. Oh, it even tells you volume. What? It's like it's a nice problem. Okay, we've got volume of 7.75 liters. And then we're actually asked to calculate pressure, so this one kind of gives it away for free. But if it doesn't give it away for free, you look for the one that's missing. So you always have to have 4 out of the 5 in your gas laws problems. And the only mystery to that, like I said, then is some wacky wording to make you really work at it. And then remember our R, our gas law constant, is always going to be the same. Even though if you grab a unit conversions table, you're going to see more than one gas constant. I think you can see probably up to 4 or 5 of them. I'm going to use the same one all the time, so let's write that one in. We're going to use the same one, and that is because of our units. So our unit conversions have to match our gas law constant. That's why they're different. If you look at the other ones, there's a couple that you may want to use in physics, and that might be joules per Kelvin mole. You're just going to have some different units in there. So in our gas laws, we're going to use this one. So I'm going to just go ahead and write that in. And then what's awesome is that is a reminder that our volume needs to be in liters. It is. We're good. Our pressure that we're going to calculate will end up in atmospheres. Okay. Because we're going to cancel everything else. Our temperature has to be in Kelvin. We are going to have to do a unit conversion here. And then, of course, our moles, wait for it, it's a cliffhanger. It's going to be in moles. Okay. So out of this one, this is why I like to just spell all this out. Take 2 seconds, spell out what your problem's telling you, and then you know your unit conversions also. So we are lucky in this one, we only need to do 1 unit conversion. So let's write it right underneath there. We've got 45 degrees Celsius. Grab your unit conversions table, and what you'll notice is if you're gonna convert that to Kelvin, you're going to add 273 to that, okay? And that is going to equal our Kelvin. So grab your calculator. What is that going to give us? I am getting 318.15 for Kelvin. All right, so now all my units match. And the other reason I like to spell it out like this is it also tells you, if you're rusty on your algebra, okay, I need to take my entire PV equals nRT, and I need to rearrange and solve for P. That's the one that we're missing. So in this one, not too bad. If you need to solve for P, let's go ahead and put volume down there. Awesome. Now, gas laws are my favorite. We literally just plug and check. So we figured out all the hard stuff. We've got all of our variables right over here. Now we just plug them in and plug it into your calculator. So my moles is 2.54. Okay, my gas law constant. Oh, I'm going to run out of a little bit of space. Okay, liters, atmospheres, moles, Kelvin. I'm going to have to continue just a little bit down here. All right, we're going to multiply that. Let me move it over to this side then. Let's multiply that by our 318. Okay, we need to multiply all of that, and then we're going to divide it by our volume. All right, let's take a second, especially on this first problem, and let's just check out our units. Okay, liters. Oh, that was way too bold, huh? That was like an angry cross out. Okay, not angry. Liters, there you go. Moles, there you go. Kelvin, done. And what's left? Atmospheres. All right, grab your calculator. Let's see what we get. All right, let's take that 318 times our moles times our gas constant, and then divided by our volume, and I get 8 point, I'm going to go ahead and round here, 56, and then my units that are left are atmospheres. Awesome. I feel like we need a sparkle pen for that. There you go. All right, so literally with our gas laws, I'm going to follow the same procedure for all of them. Let's take the funny wording right out of the equation and just spell out everything we've got, and then let's double check for any kind of unit conversions, and then let's plug and chug. So it really is, I'm going to follow that same pattern for all of them. So let's do another one. Let's try the same process and let's see what we get. Okay, now this one looks fun. We've got a sample of N2O gas. Right there, it's a gas. Anytime you have gases, you've got to use the gas law. Oh, density. Now we're getting a little bit sassy. Well, hang on a second. Where do we put that? In here. I don't know yet. Let's do that last. How's that? All right, and then we've got 298K. Okay, start with the easy one. And that is telling us that we have 298K. That's our temperature. Done. And then the question is asking us our pressure, but in millimeters of mercury. Son of a. So we already know we're going to end up with atmospheres, but then we'll have to do a unit conversion to millimeters of mercury in the end. Okay, well, son of a gun, how in the world are we going to get the other ones? Well, we know this one. And that's liters, atmospheres, mole, Kelvin. So how are we going to get moles and volume? Remember, you've got to have 4 out of 5. So we're going to have to do something with this 2.85 grams per liter. Okay, well, hang on a second. We know from last unit that we can convert grams to moles, right? So let's do that. And we could convert that to moles. And then liter, so what our density is saying is we have 2.85 grams in 1 liter. So let's go ahead and put a liter down there for our volume. There we go. All right, so now we just filled in 4 out of 5. We're going to have to do a unit conversion. So we're going to have to take that 2.85 grams and we're going to have to convert to moles. All right, now we have our molecular formula, N2O. So that means that we can just bust out our unit 3 material and calculate moles of N2O. So I'm going to go ahead and round on this one just a little bit. I'm going to do 14 for nitrogen, so 2 times 14 plus 16 for oxygen. That is 44 grams. So that means our moles then. Awesome. I am getting 0.06, and I'm going to round up to 5. Awesome. All right, so now we've got that in there. Let me go ahead and just write that number in there. We've got 0.065 moles. Okay, so now we've got everything we need right here. Now we're going to solve for pressure. So in our PV equals nRT, we're going to solve it just like the last one. And I'm going to leave pressure. And I'm going to take my nRT over volume. And this time I'm going to give myself a little bit of space and start over here, even though it looks just a little bit cramped. And I'm going to try and write just a little bit smaller. All right, what are our moles? 0.065. All right, our constant. Liters, atmospheres, mole, Kelvin. It's just a constant reminder of your units. And then our temperature, 298 K. And then let's divide that all by 1 liter. All right, double check your units. We've got liter, gone. We've got moles, gone. Kelvin, done. All right, let's solve for pressure. Just, just like you're feeling at the end of the semester, just a little bit of pressure. All right. 0.065 times 0.08206 times 298, all divided by 1. I'm getting 1.59 atmospheres. All right, now we're almost there, almost there. We have pressure, but we need to do a unit conversion. So I'm going to convert my atmospheres to millimeters of mercury. And I know that seems like a weird unit, but actually how we used to measure pressure was a manometer, and that manometer was liquid mercury. On the periodic table, all of our elements, out of all of those elements, there's actually only 2 of them that are naturally liquids, and that's bromine and mercury. And mercury, you could get your hands on back in the day, and what they would do is set out a glass kind of petri dish of mercury and invert a tube and stick it in there. And then however much the mercury rise in that tube is the pressure exerted by the atmosphere. So that is where that millimeters of mercury comes from. It's pretty cool. I mean, that's why, back in the day, a lot of your thermostats and then your manometers and your barometers and all kinds of things had mercury in them. That's why. All right, so what is that unit conversion? Well, we have 760 millimeters of mercury for 1 atmosphere. So let me grab my calculator and let's do that. And I get, all right, I get 1208.4 millimeters of mercury. Okay, I love it. So let's put a sparkle pen on that one. Done. Okay, brilliant. All right, let's do another one. What do you think? Aren't these actually kind of fun? Once you just put a little bit of work in, they kind of solve themselves. So let's follow our same process. Here's my PVNRT. Oh my gosh, do you notice I'm adapting? I'm getting smarter and I'm writing it over here more. Okay. So we have an experiment that shows 248 milliliters of gas. All right, done. I know exactly where that's going. That's our volume. Again, if you're not recognizing units, shoot, cheat on this one. It's right on your unit conversions table. That's why I handed that one out in the first day of class, because it's literally grouped by type. So you have a whole block of volume. So if you can find your unit, it's telling you right there it's a volume. All right, then we've got a mass right here. Well, we already know we can convert between moles and mass. So let's put that down here, but we have a little note that we need to convert it. So we need to convert that to moles, okay? And then we have a pressure of, there's millimeters of mercury again. We know how to convert that now. So let's put that for pressure, 745 millimeters of mercury. We know our gas constant. And I'm going to take a wild stab in the dark that, hang on a second, boy, we even have a temperature. What? What are we going to solve for? I better actually read the problem, huh? All right, and a temperature here of 28 degrees Celsius. And we already know we're going to convert that to Kelvin. Okay, son of a motherless goat, did my little process just fall apart? I've got 5 answers for all of them. Okay, well, all right, what do we need to convert? We need to convert pressure to atmospheres. We need to convert volume to liters. So we've got a little bit of math to do here and here. And here we need to convert grams to moles. Okay, how do we do that? Oh, there it is. There it is. What? That's so fun. Put a sparkle pen there. You know what? We can't convert to moles because we don't know what the gas is. Well, son of a, it's just a gas sample. In fact, for the last 200 years, this was a really common way to calculate. You could weigh your balloon, and then you used your gas law to calculate moles. So you could take a mysterious substance and calculate the molecular weight. And that's exactly what we are going to do in this question, is calculate the molar mass. So do you see why I can't convert here? I don't know the conversion because I don't know what the gas is. So what does that mean for our PV equals nRT then? It means that we're actually going to solve for this one. We're going to solve for moles. All right, so let's do our unit conversions. Let's get ready, get all those numbers ready. We have 745 millimeters of mercury. We need atmospheres. So we've got 760 in every atmosphere. So let's grab our calculator and solve for that one. So I get 0.98 atmospheres. Okay. And then let's convert 248 milliliters into liters. So there are 1,000 milliliters in a liter. Boy, that doesn't even look like an L, does it? So I'm going to get 0.248 liters there. I cheated. I didn't even use my calculator for that one. And then our temperature, 228 plus our 273. And let's see what we get. I get 301.15 Kelvin. All right, let's take our PV equals nRT, and this time we're going to solve for N. So that is PV over RT. All right, I am actually going to scroll down just a little bit, and I'm going to solve right over here. We've got PV and we've got RT. Okay, let's plug it in. I'm going to just give myself a little space here. All right, what did our pressure come out to be? 0.98 atmospheres. Our volume is 0.248 liters. Our constant. And our temperature was what, 301? Oop, not a 2. All right, double check your units. Okay, liters, atmospheres, Kelvin, Kelvin, and we're left with moles. But wait, moles are on the bottom. Isn't that the inverse? No, it's the inverse of the inverse, so we're good. Okay, so then what is our N? I'm going to grab my calculator quick. 0.98 divided by 0.08206 and 301. All right, I get 9.8 times 10 to the negative 3 moles. Now remember, this is one of those math examples we did in the very beginning of the semester. You've got to be conscious of your orders of operation on this one. And if you're using parentheses, awesome. If you're not, remember that number is a divide, not a multiply, if we're getting different numbers. Okay, so now let's take this of our gas. And now our question's asking us the molar mass. Well, what are the units for molar mass or molecular weight? We just did this in the last unit. So our molecular weight, remember our units, are grams in a mole. Okay, well, we actually just solved for mole, and we were given grams. So let's just plug it in. We were given that 0.433 grams of whatever this gas was is actually going to give us 9.8 times 10 to the negative third moles. So let's do that division, and that is our answer. Oh, I don't know what in the world I just did, but I just messed up my calculator somehow. I hit a function that I've never seen. Let me grab another calculator. Isn't that awesome? Let's take and try this again. All right, let's take our 0.433 divided by 9.8 to the negative third. I get 44. I'm going to round it to 0.2 grams per mole. So whatever this gas is, it has a molecular weight of 44. That's awesome. Maybe it's something like carbon dioxide. That's 44. There's all kinds of ways you could get to that. Okay. All right, I love it. Let's try and do another one. I think we've got one more here, and we're sassing that up a little bit, and I may have to use a different calculator. Isn't that ridiculous? You know, you press a button and all of a sudden you're in some weird function. Okay, so let's try this again. Let's use our process, PVNRT. All right, we are given 4.5 grams of chloroform. Done. We already know that's going to go under moles. Okay. Oh, the plot thickens. Now we're given another gas, 1.75 grams of methane. Huh. Okay, assuming both compounds remain as gases, okay, what pressure, dang it, that was a giveaway, okay, in a 50 ml container, so that's a volume, at 295 Celsius, there we go. Let's add in our gas constant. And now we know we're solving for pressure. Okay, so what are we going to do here? All right, pressure is what we're solving for. We need to do a unit conversion here into liters. Now, what in the world are we going to do with these? Well, this time we know what kind of gas. So grab your calculator, let's convert them to moles. So let's take our chloroform and let's convert that to moles. and that is 119.5 grams. So I get 0.034 moles. Let's do the same thing for our methane. All right, what's our molecular weight of methane then? 16. So we get 0.109 moles of chloroform. I love it. Okay, now which one do we use? Okay, but here's the beauty of Avogadro. We're going to use them both. It doesn't matter what kind of gas. It just matters how much you have. So let's add them. Our moles will be the total. So when you add that up, how many moles do we get? I get 0.143 moles total. You know, you have one of these in your homework. You add up those total moles. Okay, so that would mean our moles then, 0.143 moles. We've got that. That's our total. And then let's just do our quick temperature conversion. I get 568 Kelvin. Okay, beautiful. We've got our PV equals nRT, and we are solving for P this time. So we are ready. All right, let's plug everything in. I'm going to take that combined moles, take my gas constant, and temperature, 568 Kelvin. And then we're going to divide. We can't put milliliters in there. What are our liters? 0.05 liters, divide by 1,000. And what kind of pressure do we get? Ooh, that's huge. I get 133.4 atmospheres of pressure. Oh my gosh, that one was fun. Remember, that's the beauty of Avogadro. It doesn't matter what your gas is. Remember, it matters how many moles you have, how much is in there, how many physical atoms are in there. Okay, I think I just left myself extra space there. All right, awesome. So we just did several problems with the ideal gas law. So I'm going to stop this video, and then I'm going to have our next video. We're going to take exactly this process and apply it to a chemical reaction. It's going to be super fun. And then we'll bring in STP. So we'll do examples of our ideal gas law at STP and not at STP. It's going to be super fun.